Well, hello everyone. Thanks for joining. Welcome to my living room for this talk on PAC-Bayes. I really wanted to give a very brief overview of what PAC-Bayes is. So the very first part will mimic largely the ICML tutorial I gave last year with John Taylor. And the second part is more of a walkthrough through some recent results. So I think I know most of you, but for those of you I haven't met yet, I'm very happy to meet, even virtually, so greetings. I'm a member of the AI Center. I've moved to London a year and a half ago from France, so you probably gathered from my accent that I'm French. And I'm also affiliated with INRIA, which is a top French institute in computer science and mathematics. As such, I've been at the initiative of this INRIA London joint lab, for which we'll have a kickoff in September, so stay tuned on that. And occasionally, I'm also with the Turing Institute. When we're not all working from home, you can find me at High Holborn. I'm sitting in office 125 with John. And my key interests are really about theoretical machine learning, I would say, PAC-Bayes, obviously, hence the reason for that talk. I'm also very interested in computational statistics. I've worked on that during my PhD in Paris a few years back. Generalization bounds for deep learning. I'll comment on such results in a moment. But I would say machine learning at large. More recently, I've been more focused on what sleep deprivation can have as an effect on an academic career. So here's my 2 data points for that particular task. And moving on to, let me just mute the emails. Right, that's actually Mark writing to me. Hi, Mark, I see you're also on the talk. So what could you expect from that talk? I will give you a brief overview, as I was saying, of what PAC-Bayes is. I will try and in particular illustrate the flexibility of the PAC-Bayes approach to several problems in machine learning, and how it can actually help a lot to rethink what generalization means for many algorithms. I'll cover the 3 basic key ideas. I'll also give a glance at a few results, but I will not dig into too much details. I'll do as much as time permits, but I'll also focus on some more recent contributions from my group. So I've picked ranking, non-ID problems, deep neural networks, and contrastive learning, but I'm very happy to elaborate on different topics afterwards. What I won't do, though, is, as I was saying earlier, to cover actually our ICML tutorial. So here's the link if you want to have a look. You got the slides and videos. And we also have a new RIPS, it was NIPS back then, workshop in 2017, which features about a dozen talks where you have as well slides and videos for most of them. So you're welcome to have a look if you're interested. So I will start by really giving you the take-home message. What I want to defend as a claim is that PAC-Bayes is a very generic framework, as you will see. It allows to rethink what generalization means for many machine learning algorithms. In PAC-Bayes, you get a Bayesian flavor, as the name says, and this Bayesian flavor actually is leveraged to address the flexibility of Bayesian learning and derive new learning algorithms. So in that sense, PAC-Bayes acts as a very principled way of deriving new algorithms. I'll comment on this in a few slides. If you're interested in that, please get in touch. Please spread the word as well. If you know people who would be interested in joining, we have many openings. Right, so the first part is a subsample of our ICML tutorial with John. So you get the link over here. And there's also a survey paper which has been published. It's in English, be assured, but it's been published in the Journal of the French Mathematical Society. So you can have a look at that as well. So the first claim I'd like to start with is that learning truly is to be able to generalize. So you all know that kind of picture. This one's taken from Wikipedia. The generalization problem is from a limited number of examples, even though that number of examples is large, from a limited number of examples, what can you actually learn about the underlying phenomenon? What's happening under the hood, if I may say? And usually, I mean, you all know that if you memorize what you've already collected, if you memorize all data, this is usually pretty bad, and this leads to overfitting. Generalization is the ability to avoid overfitting. So from limited data, you learn an underlying pattern, and this allows you to perform well on future data and not directly mimic what you've already collected. So in that sense, generalization is really the ability to perform well on yet unseen data. You're going to collect more data in the future, and generalization gives you guarantees on your performance on those future data. And statistical learning theory is really all about that. It's about high confidence in that respect. Consider this example. So you fix a learning algorithm, you pick your favorite one, say the Lasso or naive Bayes or whatever. You fix your function class, you fix the sample size, so M is not allowed to grow in that example, and then you just generate new samples with M data points. And you're looking at the distribution of test errors. What would be very natural to do is to look at the mean of the error distribution, right? But that can be misleading, obviously, because you're just basically reducing the whole distribution of that to the mean, and it doesn't give you any clue on the future performance of the algorithm. So statistical learning theory is really all about understanding what happens in the tail of that particular distribution. So in statistical learning theory, SLT for short, you will be finding bounds which hold with arbitrarily large probability of a random samples of a pre-specified size, say M. And if you compare it to, for example, a statistical test, the kind of bounds you'll be interested in will give you answers such as, at 99% confidence, this is what's going to happen. The risk, the particular error of a learning algorithm will be upper bounded by some quantity with a confidence level, which is arbitrarily high. And this gives rise to the PAC framework. I'm sure most of you are familiar with that. The PAC acronym is, so that stands for probably approximately correct, and this is due to Valiant in 1984. In particular, Valiant has published a book in 2013 called Probably Approximately Correct, which is fantastic. Cannot recommend this enough. And so what a PAC inequality means is, with a confidence parameter delta that you fix beforehand, you will control the probability, depending on the sample, that you commit a large error, and this probability will be upper bounded by delta. So that's the tolerance threshold that you allow for your system. So hence the high confidence, you then take the reverse event, and you get that the probability of being approximately correct, approximately because you will have a small slack term, I will comment later on. This probability is getting closer and closer to 1 as you reduce delta. Right. So in mathematical notation, what does that mean? Well, let's assume that you have a learning algorithm. So your learning algorithm just takes data as input and then delivers a function, h. So h will be my notation for the hypothesis class. I'll try to stick to this notation for the entirety of the talk. Let's assume that you're just addressing a supervised problem. We can extend that also to unsupervised, but for the sake of concision and readiness, I'll just keep this supervised. So you get a set of inputs, a set of outputs. This is all very classical. And then you collect a training sample. So SM is just a collection of copies of X, Y. And we're just going to assume that those examples are IED. Again, we can relax that assumption, but for now, let's just keep it. It makes things much easier. And the crux is that you obviously don't know the unknown distribution, the data generating distribution over the sample. So what you're interested in is trying to infer it and trying to mimic its performance. So what can you achieve from there? Well, you can do two things, basically. You can, from that data sample, you can learn a predictor and you can certify its performance. So by learning a predictor, I mean that you can have an algorithm A, which is driven by learning principles, for example. So you could rewrite a lot of classical machine learning algorithms as minimizer of some criterion over the data. You could also add already a Bayesian flavor to it if you want to use some prior knowledge. This might result in inductive bias, so you should be careful about that. But nevertheless, you can just add this into your learning system. And once you've learned the predictor, you can still use the same data sample to certify its performance. And that gives you hints on what will happen beyond the training set. So if you do collect new data, how will your algorithm behave? And ultimately, compute generalization bound. That's what we're interested in. And actually, those two goals they interact a lot, right, with each other. So you will see the interplay in the next few slides. So I've been talking about performance. Let me just clarify what I mean by that. So we usually use risk measures. So that quantifies the error of your learning algorithm. Again, this is all very classical notation. So I'll be using a loss function. So you have your input x, you have your output h, and you're trying to find a good function h for which the discrepancy between h of x and y is not too large in some sense. So candidates loss functions are the quadratic loss function, 0, 1 if you're in binary classification. You could think of many, many losses really. And what you do compute, because this is still a random variable, right? H and x, x and y, sorry, are random variables. H will depend also on data, so that depends on random variables. So all of this is random. So you usually use, to compare different hypotheses, you usually use empirical and theoretical risks. So the empirical risk, I refer to it as the in-sample risk. It's just the error, the empirical error on the data set. And the theoretical counterpart is just the expectation. That's the expectation with respect to the unknown distribution P. So in practice, you cannot compute that term. And here's a few examples. So we've mentioned 0, 1, square loss, the hinge loss, log loss if you're doing density estimation, and so on and so on. Right, so what is generalization with those notation? Well, the question you want to address is if I have a predictor H, which is actually very good on my data set, so it does well on the in-sample pairs, will it still do well on the out-of-sample pair? So if I collect new data, what will be the performance of that particular algorithm? So the generalization gap, as we define it, is simply the difference between both quantities. So that's the error, the actual error computed with respect to the unknown distribution, and that's the performance on the particular data set you have. And from that, we're mostly interested in upper bounds and lower bounds. I will mostly comment on upper bound in that talk. So with very high probability, arbitrarily large probability, really, you want to upper bound that quantity by a term which is explicit and which will typically depend on how many data points you have, the tolerance threshold that you've given yourself, and also measures of complexity. So if you rewrite things, that gives you that. This is an upper bound on the out-of-sample risk. So this you can compute, but hopefully you will be able to compute those terms. So that will give you a number which with very high probability will upper bound this one. So we can also work on lower bounds. I won't comment on that in this talk. And there's a lot of flavors to those results. So distribution free or dependent, meaning that you can actually have particularization of these results depending on the assumptions you make on distributions, either of data or algorithms. And it could also be algorithm free or algorithm dependent in the sense that this could hold for any H, or this could hold for a particular H in which you're particularly interested. Right, so how is that? I mean, if you're already working on statistical learning theory, I think you're sold to the idea. But for those of you who aren't, how is that an interesting problem and why you should care about generalization bounds? So here's my take on why I think it's interesting to know about generalization bounds, even though you're not on statistical learning theory. Well, first of all, it really gives you a safety check. I like to think of generalization bounds as really a safety check for your algorithms. It gives you a theoretical guarantee, as you will see, on the performance of a learning algorithms on any data you will collect in the future. So you give me an algorithm. If I have a generalization bound for that particular algorithm, then you're able to compute a number, which is the largest error you will commit with a probability that you control, say 95 or 99%. And these kind of bounds actually may be computed with a training sample only. So you don't need to split your data. You don't need to split your data into training and testing. You can just compute all the bounds with the training set that you've collected so far. It gives you a control which is in most cases computable. So I will comment on this in the next few examples. And it does explain why specific learning algorithms do work in particular settings. So if you're able to compute a generalization band for which you show a very tight upper bound, it gives you the theoretical guarantee that the performance of your algorithm will be good on future data. As it is an upper bound, it does not explain why algorithm might fail. For that, you need a lower bound, but that's out of the scope of that talk. And as I was saying earlier, it also leads to design new algorithm. That's in the next few slides. Okay, before we dive into PAC-Bayes, let me give you a very brief example of a generalization bound. If you have, so let's assume you're in a very simple case where your hypothesis space is just one function. Okay, it acts as a building block for the rest of the theory. So you have one function h, and you're able to prove that with probability larger than 1 minus delta, the out of sample risk is bounded by the in sample risk plus this term, right? So as you collect data, as you collect new data points, m will increase, and this will actually go to 0 at the rate 1 over square root m. So this is a very classical result in statistical learning theory. What happens if you have a finite number of hypotheses? Well, you can hint what happens. This is just a generalization of the earlier result. You just pay in the log, you just pay how many functions you have in your class. So if you have a class which has a finite number of functions, say, even if it's a very large number, even if you have 10 to the 10 functions, you just pay that term actually through a log, and the rate of convergence with respect to a sample size is still the same, is still 1 over square root m. So what those kind of results tell you is that for any predictor in your class, you get the assurance that the error on the theoretical error will never be larger than the error you commit on your particular sample plus this term that you can always compute, right? If we extend this a bit further, this opens the way to structural risk minimization. So this is all classical results from the 80s, 70s and 80s, in particular with people as Vladimir Vapnik or Alexei Shavanenkis and many of their co-authors. The structural risk minimization framework gives weight to hypothesis. So if you have hypothesis HI, which is associated to a particular prior weight PI, you see that from the previous formula that you have a term which will weigh in any particular predictor. So this holds for any particular HI, and the bound is different. That was what I was alluding to when I said that those kind of bounds could have flavor of algorithm dependence. So this is a particular example. And then if you extend this, because obviously we want to have the most general results in that respect, if you extend this to uncountably infinite function classes, then you resort to complexity measures such as the VC dimension or the Rademacher complexity terms. I'm not going to give examples of those bounds, but you can find some in our ICML tutorial. And those approaches are really suited when you want to analyze particular predictors. So as those functions actually hold, regardless of the predictor you pick in H, you can just pick your favorite one, and then you have a generalization band which helps you understand the performance of that particular algorithm. That's, I mean, I guess you could see the transition. What we will be interested in is to try and take account of the correlations between predictors. What if you have a gigantic hypothesis class and you really don't know which one you want to pick? Well, you'd be interested in maintaining something more rich, possibly on the space of distributions. And that's what PAC-Bayes does. PAC-Bayes is an extension of that framework, and it maintains distributions of hypotheses. So you no longer pick hypotheses manually, should I say, but you're rather maintaining probability distributions of a hypothesis. And that's what makes the difference. So what is PAC-Bayes? So PAC-Bayes is really providing PAC generalization bounds for Bayesian flavored estimators, right? And the name is pretty transparent in that respect. So here's how it works. So that's my one slide on what PAC-Bayes is. So before you collect data, you usually fix the distribution P. It's a reference distribution, a reference measure. We often call it a prior to be consistent with Bayesian statistics, but as you will see, it can actually be something else. It does not need to be a prior in the true Bayesian sense. Based on your data, you then learn a distribution Q, which is a distribution inspired by what we call the prior. So again, to be consistent with that posterior, but that's really a distribution which is taking into account the data. And if you want to do prediction from there, you actually draw a fresh sample. So you draw a new hypothesis, H, you sample this from Q, U posterior, and you predict with that particular function H. So each prediction you make is a fresh random draw with that matter. So we need now to adapt a bit the risk measures. So previously I had the in-sample risks and out-of-sample risks for hypotheses. I will now extend that notation to average of a distribution. So it's now just the integral of the in-sample risk with respect to the distribution of a hypothesis and the out-sample risk as the integral of the earlier out-of-sample risk for each hypothesis. So you're now comparing risks not of hypothesis, but of distributions of a hypothesis. A good way to measure also discrepancy between those objects is to use probability measures divergences. In particular, the Kullback-Leibler divergence is one of the most popular. You will see that we can use different ones, but this is definitely one of the most popular. So let's stick with the KL for now. Another claim I like to make, and we certainly did it in our tutorial with John, is you could see what happens in PAC-Bayes as a generalization of the Bayesian update principle. So here's, again, I try to convince you in what slide. So so that's what is happening in Bayesian inference. I should say that I'm a trained Bayesian. I've been doing Bayes statistics in my undergrads. So I come from that framework, really. In Bayesian inference, what you do is you specify prior, right? You specify actually a statistical modeling. You have a probabilistic modeling of the phenomenon you want to study or you want to predict for. And that gives, so this is usually encapsulated within the likelihood function. And then from the prior and the likelihoods, you get a unique way of deriving a posterior. That's the Bayes update rule. What happens in PAC-Bayes? Well, it is model free in the sense that there is no statistical modeling. There is no likelihood. There is just a loss function. So you could argue that specifying a loss function induces a statistical modeling. This is true in many cases, but not in all cases. At least the statistical modeling might not be explicit. So in that sense, PAC-Bayes is really a model-free approach. You don't need to specify the kind of dependence between X and Y beforehand. You're just interested in, when you collect X and Y's, you're just interested in the performance through the loss function. It is inspired by the Bayesian update principle because from a reference measure, aka the prior, and the loss function, you derive another distribution, which could depend on data. You will also see that you can moderate the dependency on data with a temperature parameter, for example. But you will be interested in distributions which possibly depend on the data and which, again, do not correspond to a particular Bayesian model. So in that sense, we call this prior and posterior, but I really like to think in PAC-Bayes as the prior, as an exploration mechanism, really, of your hypothesis space. And the posterior is just the way that reality twists your prior. So you have your prior distribution, you collect data. As long as you collect data, you actually confront your prior knowledge with the world and experience, and then you beginning to build up a posterior, which is your updated belief on the world after confronting your prior knowledge, your prior beliefs, and data. That is what it is. So yeah, we like to think of what's happening in PAC-Bayes as a generalization of the Bayesian principles. To go further in the comparison, what happens in PAC-Bayes bounds versus what you have in Bayesian learning. So the prior in most PAC-Bayesian bounds is actually left to the choice of the user. So all bounds hold for any prior distribution, whereas in Bayesian statistics, you usually pick a particular prior, and this impacts a lot your inference strategy afterwards. The same goes for the posterior. You will see that all PAC-Bayes bounds hold for actually any posterior distribution, whereas in Bayesian statistics, the posterior is uniquely defined by the prior in the model you've put through. As for the data distribution, same goes for PAC-Bayes. This holds for any distribution. So in a sense, it's very generic, right? There is no assumption, particular assumption or restrictions on prior, posterior, and data distribution. Okay, now time to move on to one PAC-Bayesian bound, so the earliest one really. The prehistory of PAC-Bayes is actually due to John and co-authors, so Bob Williamson in particular, in the paper in '97. But the true birth of PAC-Bayes is due to David McAllister in a series of court paper in '98 and '99. So here's the rewritten form of the McAllister bound. So what this means is for any prior P, in any confidence threshold delta, so you pick delta, remember, then you get that the probability, depending on the underlying distribution, of the outer sample risk being upper bounded by this quantity is larger than 1 minus delta. Okay, so you pick delta, you can compute the empirical risk on your data set, then you get the KL, which might be intractable in some settings, but let's assume that we can compute it for now. And then you get this term, which features the confidence level. What this tells you is that no matter the distribution you pick on the hypothesis, no matter the posterior that you pick, Q, its error in the sense of that risk will never be larger than this quantity. So that's the first PAC-Bayes bound. It's PAC, as I was saying, and it's Bayesian flavored because you're not comparing a hypothesis, but rather distributions of a hypothesis. Right, just to illustrate, so brace yourself, there's a lot of citations and references coming in those two slides. Just to illustrate how flexible PAC-Bayes is, I just want to emphasize how many fields it's been applied to. So obviously statistical learning theory with a lot of papers from John, Matthias Seeger, Olivier Catoni in France, and many others. But PAC-Bayes has also been used also by John to understand how SVMs, for example, or linear classifiers operate. There's a few supervised learning algorithms which have been reinterpreted as minimizers of PAC-Bayes bounds. I'll give an example later on. This has also been applied to high dimensional regression, so additive regression, single index models, ranking. I'll touch a bit on ranking afterwards. Classification, obviously, transductive learning, domain adaptation, non-ID heavy tail data. This has been a very recent effort in the PAC-Bayes community. There's a few work on trying to go towards even more realistic assumptions on data. You could also go PAC-Bayes with density estimation. There's a few contributions also in RL. I know that's of interest to many of you. There's PAC-Bayes attempts to sequential learning. There's been a few connections lately by Dan Roy and his group, in particular with algorithmic stability, differential privacy. Obviously, there's also a big surge of interest with deep nets. And I'll show you an example of a generalization bound inspired by the PAC-Bayes approach for deep neural networks. So my point with this list of reference is to show you that as long as you can define a loss function, and as long as you can define probability distributions of a set of hypotheses, you can go PAC-Bayes. Those are the only two prerequisites that you need to try and use the PAC-Bayes approach to any particular learning problem. Right. Let's move on now to PAC-Bayes inspired learning algorithms. So I've been claiming earlier that you can use PAC-Bayes bound to derive new algorithms. So here's how it works. So this is a prototypic form of generalization bounds. the error on unseen data is appended by the error on the sample and a complexity term. And this defines actually a very principal strategy. If you want to find new algorithms, you just minimize the right-hand side of that inequality. So you will be minimizing with respect to Q, where Q is a probability distribution. So in a sense, this is really akin to regularization, right? When you minimize an empirical criterion plus an L1 norm, for example, when you're computing the lasso, you're not doing something else. You're doing exactly this kind of strategy. What is different there is that you're minimizing objects on probability distribution spaces. So rather than the L1 norm of a vector of weights, for example, you're minimizing the KL between between the distribution you're optimizing on and a reference measure prior. But this really is the same strategy. And this is an optimization problem for which there's a lot of techniques in the literature. So I've been mostly interested, particularly during my PhD, on MCMC methods, Monte Carlo Markov chain. More recently, I've started to try and look at that as a variational inference problem, and you could also go with SGD or any other gradient descent flavor method to try and solve that particular problem. In particular, as I was saying earlier, the SVMs, KL, AdaBoost, the exponential weights, they are all minimizers of PAC-Bayes bounds. So it's interesting really how those algorithms, which are not connected to PAC-Bayes whatsoever, have been reinvented in the PAC-Bayes community as minimizer of generalization bounds. Okay, just keeping track on the time. So maybe I'll try and move a bit faster on that part. That's one of the key results in PAC-Bayes. It's the variational definition of the KL. This is a result due to Imre Cizar and Dunstan Varadan in 2 separate papers in the 70s. It's been reinterpreted in the PAC-Bayes framework by Olivier Catoni in his book in 2004. And let me just give you the statement. Maybe I'll skip over the proof in the interest of time. But what this result tells you is an explicit formulation for the log of the integral of the exponential of any function with respect to the prior. This can be rewritten as the sup of the integral of phi with respect to the posterior minus the KL between both distributions. This is a Legendre transform of the KL. It's also known under that name. That's the first part of the statement. The second part of the statement is that this supremum is actually achieved by one very particular distribution. I'm pretty sure most of you know it. It's the Gibbs measure, or the Gibbs potential. So the Gibbs measure is simply the exponential of any function renormalized. And that Gibbs potential or Gibbs measure is the optimal point of that particular constraint problem. It's actually unique and defined to be the Gibbs. So the proof is really elementary. I'll go very quickly over it, but that's the recapitulation of the statement over here. We're trying to prove that, and that's the definition of the Gibbs. So if you assume that the Radon-Nikodym derivatives make sense, so for that you need that Q is absolutely continuous with respect to P and vice versa, then elementary manipulation really of those quantities just give you that if you artificially introduce TP in that inequality, you linearize the log, then you remember that this is exactly the KL between Q and P, and you just write what the normalizing constant of this particular distribution is. Then you remember that the KL is a divergence, so it's non-negative. And so as a function of the first argument, it reaches a maximum in the second argument, obviously, and this maximum is 0. And that gives you the result. It's a very simple and elementary proof. In the context of PAC-Bayes, what if I now pick a temperature lambda and I pick this phi function to be minus temperature times empirical risk? Then this is just the Gibbs posterior that most of you are familiar with. And if you write that statement for that particular Gibbs posterior, then you find that this distribution Q lambda is the one minimizing the empirical risk plus KL times a parameter lambda. So this is exactly what I was saying earlier. You're just minimizing an empirical criterion plus a KL between distribution. And this is really akin to regularization in regression. Right, so that closes the first part, which is a very condensed, I should say dense, I hope I haven't lost too many of you, on what PAC-Bayes is. So what we've seen so far is that statistical learning theory is really about controlling the tails of the distribution of error. So it's really about high confidence results on generalization. And I hope I convinced you that PAC-Bayes, among the different ways of addressing generalization, PAC-Bayes is a very generic and powerful tool to understand what's going on. It can also be leveraged to create new algorithms with a Bayesian flavor, because again, you're maintaining distributions of hypotheses. And I think it's a very exciting field. So I've been working on PAC-Bayes for more than 10 years now. It was definitely not very cool 10 years ago. I'm not claiming it's super cool now, but it's definitely cooler. It's getting a lot of traction. Also because it's one of the most promising frameworks to address generalization for deep nets. So there's been a surge of interest in PAC-Bayes for that reason in the past few years. And if you monitor submissions to ICML, Colt, and NeurIPS, for example, you used to have maybe 2 or 3 papers on PAC-Bayes 5 or 10 years ago, and now it's more 15, 20 papers minimum to each conferences. So there's definitely momentum happening there. What's coming next? In the next 15 to 20 minutes or so, well, a sample of what PAC-Bayes has to offer in several topics. So I guess maybe now is a good time to take a small break and take questions if there are any. No, there are not. Omar is just saying very nice. Thank you very much, Omar. That's the kind of questions I like. Good. If anyone has a question, no, it's a good time to do so.
I have a question.
Right.
Do you have any assumption whatsoever on the distributions P and Q that you can choose in terms of regularity of the distributions, or?
No. The only requirement to have bounds like that is that P is absolutely continuous with respect to Q, and Q is absolutely continuous with respect to P. So in particular, that induces that they both have the same support. Yeah, that's all.
Okay.
No other assumptions.
In case you want to, so are you allowed to have, for example, that both P and Q are a sum of Dirac deltas if the support of the Dirac deltas are the same? So basically, the set of hypotheses you consider in the end is a finite set somehow.
Right. That's a very good question. Yes, you can, but with a slightly different proof technique than the one I've just mentioned. This formula is really tailored for for infinite and uncountably hypothesis spaces. But if you remember the bounds I've given at the beginning, just before introducing PAC-Bayes, you can actually have finite results. So for those particular bounds, yes, you can have direct measures.
Okay. Yeah, what I wanted to ask is exactly this. So if in the PAC-Bayes you consider Dirac deltas basically as P and Q, you recover the same bounds as the statistical learning theory ones, let's say.
Exactly.
Okay. Yeah. Okay.
Thanks. So thanks for your question. That's another argument actually for that claim that PAC-Bayes is a generalization of the previous approaches, in the sense that because you're maintaining distributions of hypotheses, you can always pick the distributions which are degenerate, so Dirac in one particular hypothesis, for example. So you pick a Dirac in the empirical risk minimizer, and then you recover results from the classical literature. Yeah.
I see. Thanks.
Thanks. Right. Okay. If you don't have any more questions, let's move on to the second part. So probably I won't be able to cover all of it. But that was just to give you a glance of what I've been doing in the past few years with an amazing bunch of people. So that's Sylvain Robiano, who used to be at UCL in stats, Pierre Alquier, who's now in Riken in Japan, Guedj, François, and Pascal, who are all in Université Laval in Quebec, and Kent, who was visiting last year at the Eye Center. I'm sure some of you remember him. If you were there before last October, you've met him at the Eye Center. So this is just a very brief overview of 4 papers. There's I guess there's a lot of other papers I would have loved to talk about, but I just decided to focus on those 4 and probably less than 4 because I'm running short on time. But the first one is on ranking. So that's the PAC-Bayes version of high-dimensional binary bipartite ranking, sorry. The second one is about how you can tailor new PAC-Bayesian bounds with different probability divergence. So we drop the KL and state PAC-Bayesian bounds with a much wider and much more richer class of F divergences from Shizar. So the KL is actually a specific part of F divergences. So we have PAC-Bayes bounds which hold if you drop the ID assumption. Remember the very beginning, I assume that data is ID. That's convenient in many cases, but you can actually drop that assumption in PAC-Bayes. So you have bounds holding if you have data which are not ID, or if you have heavy-tailed. So in particular, you don't need to assume boundedness of your predictors. The third paper, which appeared at the last NeurIPS, is about generalization bounds for deep nets. Not all deep nets, obviously, a very particular case of deep nets with binary activation functions. And the last one is an attempt to adapt the PAC-Bayes framework to contrastive learning. This is a very hot topic at the moment. We took inspiration from a paper of Aurora and co-authors, which appeared at the last ICML. And contrastive losses are widely used, for example, in NLP. So that's yet another field of application of the PAC-Bayes framework. Right, okay, so let me just go quickly. I might actually, in the interest of time, I might actually just state actually the results and skip those very heavy notation. So that's the PAC-Bayes bound that we provide for the bipartite ranking problem. Let's just forget the notation. I'm just going to explain what the bound means. That's the bipartite ranking losses, right? So the loss in ranking. So ranking is all about ordering data samples. You want to order inputs with respect to the labels. So you're not interested in prediction per se. You're not interested in predicting the correct labels. You just want to order the labels in a consistent way. So you have a specific loss function for that. And what we do prove are the first minimax optimal rates for that particular problem. So in more details, the ranking losses are upper-bounded with an arbitrarily large probability by the optimal ranking loss for that particular class of problem, plus a term, which, as you see, involves numerical constants and just a sample size. K and D, so D is the ambient dimension of the problem. So even though you're working in problem with very high dimension, so if D is 10 to the 15, say, that's not a problem because you pay this dimension only through a log. And K is the optimal intrinsic dimension. So in a sense, it acts as a dimension reduction technique. So in the end, if you have a sparse good solution, if there exists a sparse good predictor, then the PAC-Bayes bound will find it. So it's adaptive in the sense. So what this tells you is that for the ranking problem, even in very high dimensions, you get a way of constructing algorithms which achieve a very small theoretical loss, as you have in many PAC-Bayes bounds. Right, so that was a very brief overview of that work. I'm very happy to elaborate after the talk. I just want to keep this within the boundaries of an hour.
Can I ask a quick question?
Sure.
How do you establish that this is minimax optimal? I mean, do you have a matching lower bound?
We have lower bounds. Yeah, exactly.
Okay. Cool.
I didn't comment on lower bounds so far in the interest of space and time, but yes.
Cool, thanks.
Yeah. That's focus number 2 on learning with non-ID or heavy-tail data, or both, obviously. So you just drop the 2 assumptions I've made in the beginning, which are the loss is bounded because it's convenient, but not so realistic. And you also drop the ID assumption because, again, it's super convenient in classical statistics textbook, but it's definitely not realistic in many problems. So I'll just define this quantity, which is linked to the qth moment of the generalization gap. Again, I think the important is not focused on the details, but rather on what these inequalities mean. As I was saying earlier, we'll just generalize the KL divergence to the much richer class of Shizar F divergences. So in particular, the KL is obtained if you pick a specific F function here. If you pick F to be X log X, then you recover the KL. So that's a strict generalization of the KL. And then that's our take on PAC-Bayes with F divergences. This is the result. So we show that with very high probability, you can actually upper bound the generalization gap by a term which depends on two quantities. The first one is the qth moment of the generalization gap. And the second one is a term which involves the F divergences between the prior and the posterior. So let me jump to the conclusion as well. So as a corollary, this is the form of the PAC-Bayes bound that we have. So you can see that it is similar in spirit, obviously, to the ones I've shown before. What's different here is that, so those terms are already what we have in classical PAC-Bayes band, but this one is fairly more involved. And that is the price to pay. We rephrase that as the price to pay for dropping the ID and abundantness assumption. So this bound is obviously not as tight as other ones, but it actually holds in much more realistic settings, we believe. And this, again, is also very strong incitement to define the optimal Q as the minimizer of this right-hand side. So what was very convenient with the KL, for example, was because of the Legendre transform of the KL, if you minimize this right-hand side with respect to Q, if you have a KL, the optimal Q is usually the Gibbs measure, the Gibbs potential. So that's a distribution that we're all very accustomed to, which is in many cases quite easy to implement or even to sample if you make simplifying assumptions. In that particular case, this is a nightmare to optimize and the resulting Q is non-tractable. But nevertheless, that was a first attempt at proving PAC-Bayes band in that particular problem. I just want to emphasize the interplay between having theoretical results and being able to implement the algorithm, which is suggested by the theoretical results. There's a large interplay between both. I've been very interested in both aspects of that particular problem. But I guess, I mean, there's a lot to say, really. I could ramble on for hours on that. So, okay, let's just move on to focus 3. Yes.
Sure. Just about this slide.
Right.
What if we change the Q, basically the F divergence between probabilities, the F measures with integral kind of probability measures that they?
Yes, exactly.
Yeah. Is that any? I can imagine that perhaps the right-hand side might not be as tractable as you have introduced the Gibbs sampling. I can imagine that might be one of the consequences. Yeah. But then, yeah, I wanted to know if you have tested and you've seen any difference in the behavior.
You mean in practice?
Yes.
Have we?
Yeah.
So no, we haven't. So short answer is no. The more elaborate answer is we haven't implemented that particular band because definitely it's not competitive with other bands in terms of numerical values, right? So the contribution of that work was really to show that yes, we can still have bounds even though we drop the abundantness and ID assumptions. But in practice, I would not recommend using that one.
In general case, when we really don't have a view about the IID, it's something that it's easier to identify, but we don't have a view about the tail, the fat tail of the samples. So in that case, you still prefer F measures over integral.
Yes. Yeah, exactly.
Understood. And one more small question: do we have any idea about asymptotic behavior of the right-hand side when we have the sample increases, how the behavior changes? And
for that particular bound, or for more generally?
For that.
Right. So for that particular bound, I actually removed that particular slide because I had too many slides already. But yes, if you assume, okay, so if you pick that particular bound in okay, let me get this right. I don't want to make a mistake. But if you pick, so Q and P are just integers, right? They're conjugate integers. So if you pick Q equals P equals 2, okay, then what you get on this right-hand side is morally the second moment of the generalization gap divided by square root of m. So the rate of convergence is square root of m in that particular case. If you increase P and Q, you will degrade that convergence rate. And the claims I was making earlier that this band is not competitive in the most general case is because the 1 over square root m is the least you could ask to a PAC-Bayes bound. In many cases, this degrades the rate of that particular bound. But if Q equals P equals 2, then you recover the classical rate 1 over square root m. So the asymptotic behavior of the bound decays with 1 over square root m.
Okay, thank you.
Right. Okay, so okay, see, I actually had it. Yeah. Okay, so that's exactly what I just said. If you pick P equals Q equals 2, then you get that this is upper-bounded by the square root of, so V is the variance of the generalization gap, and you get this 1 over square root m term. Sorry, yeah, I've modified those slides so much, I can't even remember where I've put things. Right, so that closes that focus number 2 on this paper with Pierre on PAC-Bayes with F divergences. I'll skip the proof, even though I think it's really elegant and super simple. I really like elementary proofs that you can fit in one slide. I don't have so many of them. Most of the proofs in my paper takes pages and pages. So I'm very proud to actually show those ones. It just relies on Jensen, this change of measure, which is classical in PAC-Bayes proofs, and then Holder and Markov's inequality. Boom. Okay, let's move on very quickly to neural networks, in particular this architecture of binary activated neural networks. So this is a standard neural network. What we used is an architecture where the sigma function is just a sine function. Okay, so you get a binary activation function. That's what's shown here. So that's the architecture we have. For that particular architecture, we have a series of tricks. I'm afraid I won't be able to comment on many of those. So let me just, I think I'll just jump to the generalization bound, which holds for that particular problem. So the only assumption we make is that we have a neural network for which the activation functions everywhere are the sine function. And it's a binary classification problem. So the final output is -1 and 1. The network is allowed to have as many layers as you want, as many neurons as you want. We just assume that it's fully connected because it's really helpful in the mathematical analysis. But what we do get in the end, so I'll just keep over this few slides which just show the approach. That's the final generalization band we have in that NeurIPS paper. The G theta is just the output of a network, so that's the whole network. The error of the whole network on any future data you're going to collect is upper-bounded with a very large probability by this quantity. So you get an infimum over the constant C, so you're optimizing all of this in C. And as in all PAC-Bayes bound, you pay 2 terms. The first one is the empirical risk, so that's the empirical error of your neural network. And then you pay the KL between theta and theta naught. So theta naught is just the concatenation of all the weights of the network, and you're optimizing in theta. So this holds for any theta. In particular, you can optimize the right-hand side with respect to theta. We've put forward a few tricks to do so. And what we've shown empirically, so this is a theoretical contribution, but we also have an empirical validation of that problem, in particular on MNIST. So let me just focus on this last part. So the lines are a few classical data sets, so I'll just focus on the MNIST one. So what we show here, just to give you a sense of what's happening, this is the training error, ES. This is the testing error, and that is the value of the bound, okay? So forget about the theory, forget about PAC-Bayes. You're not interested in that. You're a practitioner of machine learning and you have a data set and you have a neural network with binary activation functions. You compute the training error, okay? So those are the training errors, for example, on MNIST, 0.003. That's the training error. You obviously don't know the testing error, right? This is an estimate, but you never see the testing error. What PAC-Bayes gives you, if you plug this number into the bound, is that with probability larger than 99%, the error on any future sample from MNIST will never be larger than 0.009. And that's the kind of generalization guarantee that we're interested in, right? I'm interested really in the whole pipeline, from theory to practical implementation and usefulness for practitioners of machine learning. And this gives you the safety check I was alluding to, right? You compute the error on a particular data set. Okay, PAC-Bayes tells you that's how you perform on your data set. Well, on any future instance of your data set, this is how you will perform at the worst. Remember, this is an upper bound, so it's a worst case scenario. In practice, you might be lower than that. Actually, the test error is systematically lower, obviously, but that's the safety net that you have. Okay, so that closes, yeah. So that closes that focus number 3. It's 11:02. Maybe I'll just, okay, very briefly comment on the contrastive loss. So using contrastive losses allows you to compare what's happening between a supervised problem and the corresponding unsupervised problem, where you just remove all labels. And there are very few results, even though this is massively used, for example, in the NLP. There are, up to my knowledge, very few theoretical results and understanding on the performance of algorithm driven by contrastive losses. A significant breakthrough is due to Aurora and co-authors at last ICML, and they've shown this very nice bound between the loss on the supervised case, upper bounded by the loss in the unsupervised case, plus a complexity term with Rademacher complexities. So what we did was turn this into PAC-Bayes bound, which is tighter and which allows to drop the ID assumption as before. If you want more details, I think you're gonna have to invite me again because I'm just running out of time. Okay, so I think that closes my talk. Thank you very much for attending. If you're interested in other outputs from my group, I'd be very happy to chat about any of those particular papers. As you can see, not all of those are about PAC-Bayes. Actually, just a minority is about PAC-Bayes. But yeah, I hope you found this interesting, and I'd be very happy to take questions either now or after the talk. Thanks, everyone.